Okay, welcome to lesson 7. So this is a continuation of slope fields. So we're talking about Euler's method now, not Euler, but Euler. And recall with the last example that you have in your notes. So look back at that right now. Recall that we created a slope field for the differential equation dy dx equals x plus y. And we sketched the particular solution that was through the point 2, 0. So recall there, we created the slope field first, and then we identified the point that it's passing through at 2, 0, and then we drew our curve based on those little tangent line slopes. So this method is different. Instead of creating a slope field, instead what we're going to do is we are going to start at the point that we know it's passing through. The point that we know it's passing through, we're going to call xy. So down here in my diagram, I labeled that our starting point. Okay? So rather than using our slope field to draw the curve, instead we are going to use equal increments for x, which by the way, we're going to call this delta x, right? Our change in x. And we're going to piece together little line segments to build our continuous approximation of the curve. And by the way, we're not going to actually draw the curve. We're just going to be looking to identify a point on the solution curve, starting at a certain point, using this idea of building off of the start point using increments for x. So imagine we have our solution curve here down below. I drew it in black. Again, we have our starting point xy. Delta x is our change in x. So it's how far away we want to move horizontally, either left or right. So you're always going to be told what that increment of x is. So for example, it might be 0.1. All right. So we are going a certain distance for x, and then we also have a certain distance for y. Okay, our change in y. So our new point here is found by adding on our change in x and our change in y. So the big idea here, the main formula that you're going to have to remember is this right here. To find your change in y, which is going to be your new height for your point, you're going to take the slope, okay, and then you're going to multiply it by the change in x. All right, and then that's going to give us an approximation for where our curve would be. So in this case, you can see that based on my diagram, this would be an underestimate since it's below the actual curve. Okay, this will make a lot more sense once we look at an example. Okay, so here's what a typical example would look like. We're told directly we want to use Euler's method. Notice how we're given set increments of delta x, which is equal to 0.2, and we are looking to approximate f of 3, and we're looking at that same differential equation that we saw in the previous video. Okay, so again, we're not looking to draw the slope field and then approximate the curve. Instead, we're going to use this method called Euler's method to approximate this value. So to do this, it's actually not that complicated at all. All you're going to do is you're going to make a table, and the table is always going to be set up the same way. So this is what the heading is going to look like in your table. So we're going to start with our point xy. Now, we know that the starting point here is 2, 0, right? That's the only point that we know that the curve passes through. We have our derivative next, okay? And I suppose you could rearrange these columns. They don't necessarily have to be in this order, but to me this makes the most logical sense. So the derivative we know is found by adding the x and the y value. So remember, that's what we did when we created our slope field. Okay, but here we're just going to track what the actual slope value would be. So we know that when we add our 2 and our 0, right, our x and our y, we're going to get 2. We're told that the change in x is 0.2. And now to get our change in y, this is where, again, you need to know that mini formula. So we're going to be multiplying the derivative value by the change in x value. So if we apply that here, we're just multiplying the 2 by the 0.2, and we're going to get 0.4. Okay, so 0.4 is our change in y. So our new point, so this is just where you're going to add on your change in x and your change in y to the original point. So we have a starting x value of 2. We're adding on 0.2, so we have a new x value of 2.2. and then a new y value of, well, we started with a y value of 0. We're adding on 0.4, so 0.4 would be the new y value. We are then going to repeat this until we get to the value that we're trying to approximate, which is f of 3. So if we're starting at 2 and we have to get to 3 and we have increments of 0.2, you can see that we're going to need to do this 5 times, right? So what we're now going to do is take that point that we just found and we're going to transfer it over here. So 2.2 comma 0.4, okay? And now we're going to go through the same thing, okay? We're going to first find our new slope value there by adding the x and the y, because that's what our derivative formula tells us to do. So our new value here would be 2.6, okay? Our change in x for all of these is going to always be 0.2, all right, because that's the fixed increment that we're going to use every time. The change in y will be different, okay? Again, go back to that mini formula. You're going to have to multiply the 2.6 and the 0.2, and we're going to get a new y value of 0.52. So then, it's just a matter of adding those together to get your new point, okay? So we're at 2.2 is the starting x value. We're adding on another 0.2, so now we're at 2.4. And the new y value, again, we're over here, we are at 0.4. And then we're adding on the new amount of 0.52. So that's going to give us 0.92. Okay? Now we can jump ahead a little bit. We know that this next one is going to be 2.6, 2.8, and then we're going to end here at 3 because, again, we're asked to approximate f of 3. So whatever this ends up being here in the end is going to be our final answer. Okay, so I transferred over my new point of 2.4 and then 0.92. I found my new slope, all right, and again, think of the slope as your direction, okay, or your rate of change. It's telling us where to go, okay. So this is the new slope. We're going to multiply that by our increment of 0.2, so these are all going to be 0.2, okay. To find the change in y, again, we're using this formula, so you're just multiplying together the dy dx number by the delta x number, so, and you'll be allowed to use a calculator for all of these. So that's 0.664, and then when you add 0.664 to that 0.92, that's how we're going to get the 1.584. So see if you can try the next row. Okay, so take a look at that. Hopefully you agree. And then let's do it one more time. Hit pause and try it. So when we finish this up, we get 3.46496. So this is our approximation for f of 3. Now remember, this is just an approximation. We don't know what the actual function value is when x is 3. We're using this technique of Euler's method to just approximate what f of 3 would be. Again, we're using this idea of increments for x. And by the way, you'll see some practice problems where sometimes your increments for x are negative values. So that would indicate that we're moving to the left of our starting point, whereas here we're moving to the right of our starting point. So Euler's method is not complicated. All you need to do is remember this top row here, okay? And it's just a matter of, once you have that memorized, you need to make sure you know this formula for finding our change in y. And then it's just a matter of systematically going through, and usually you're not going to have to go more than 5 times to get to your value, okay? So the last number you see here will always be your approximation, okay? That's all for now. Bye-bye.